Okay, we've got a nice long answer problem here. We're regarding hydrates, measuring the masses of hydrates. So let's take a look at this. We've got ABC right here, and then we'll have D and E right after that. So we've got a data set here. We've got some data regarding a hydrate. In the first of two experiments, a student is assigned the task of determining the number of moles of water in 1 mole of MgCl2 NH2O. So we don't know that number. We don't know how many waters are in this hydrate, how many water molecules are in one formula unit of this hydrate. So we want to find out. The student collects the data shown in the following table. So we've got the mass of the empty container. We've got the initial mass of the sample and the sample and the container. So the container, and then we put that sample in there. The mass of sample and container after first heating. So we'll notice the mass has dropped because water has evaporated. And then second heating, so a little more water. We got most of it on that first heating, but a little bit more water, right, 23.976. That went down a little more. And then a third heating, just to be thorough, we see that we didn't lose any more mass, so that's the end of the experiment. So we're going to use this data to determine all of this stuff just by looking at the mass of water that was lost. So Part A, explain why the student can correctly conclude that the hydrate was heated a sufficient number of times in the experiment. So we want to heat this until all of the water is gone. And as water is leaving, the mass is going down, right? Because water has mass. So as it leaves the sample, the mass goes down. But right here, right, we see that no mass was lost. In fact, it went back up 0.001. So, that could be experimental error or whatever, but it didn't go down, right? As long as the mass is no longer going down, we can conclude that this is sufficiently heated. There's no more water there. So mass not going down. Right, so we want to explain that logic because from this one to this one, we didn't lose any more mass. There must not be any water there left to evaporate and bring the mass down anymore. So that's a straightforward one. Now let's do our calculation. So we want to calculate the total number of moles of water lost when the sample was heated, and then determine the formula of the hydrated compound. So how are we going to do this? Well, we need to figure out the mass of water that was lost. So we are going to take this one here, initial mass of sample and container. So that's the hydrate. That's got the metal and all of the water. And then we are going to subtract one of these, right? Since we didn't lose any water there, it doesn't really matter which one. So, but this is after all the water is gone. So if we subtract, we have the sample, we have the container and the sample with all the water, and then the container and the sample with the water gone, right? So 25.825 grams minus 23, let's just use 977, right? It doesn't really matter which one, it's fine. That's going to give us 1.848 grams of water. And then we can get the moles, right? It says the total number of moles of water. All we have to do is multiply by 1 mole over 18.02 grams. That's the molar mass of water. And we are going to get 0.1026 moles of water. So that is this one. So that was just, right, we need to know what these numbers are, right? We need to know that this is just the container. This is the container and the sample of the hydrate, and then this is the container and the sample with the water gone. So if we subtract this and this, we get just the water that was lost. So we get a mass of water, use the molar mass to convert to moles. Very straightforward. So 0.1026 moles of water. Now determine the formula of the hydrated compound. So what are we going to do here? We need to get the mass of the sample itself, right? So if we take 23.977 and we are going to subtract the container, right? So we're trying to get the mass of MgCl2. So here, this is just this is the container plus MgCl2. The water is gone, right? So if we do 23.977 minus just the container by itself, 22.347. That gives us 1.630 grams of MgCl2, right? Because this is with no water. This is just the container and MgCl2, and this is just the container. So if we subtract, we get the mass of MgCl2. All the water is gone. And then again, let's multiply by 1 mole over, and then we have a periodic table, so you can get this very easily, right? 95.2 grams, that's just the molar mass of MgCl2. We can get that from the periodic table, and that is going to give us 0.01712 moles of MgCl2, right? So that's very important. So in that sample, in the just the mass of the sample in the container, so the hydrate with the MgCl2 with all the water, that was this many moles of MgCl2 and this many moles of water. And so all we have to do is get the ratio, right? We want an integer ratio. So let's just do the moles of water. There's more water, so we'll put that on top. 0.1026 moles of water over 0.01712 moles of MgCl2. That gives us 5.993, which is, we can say 6, right? That's about 6. And so that means there are 6 moles of water for every 1 mole of MgCl2. So that means that this is, we'll just write it right here, MgCl2, and then the little dot right there signifying the hydrate, 6 H2O. Right? So it was very simple, right? All we did was we used this data to get the mass of water and use the molar mass to get the moles of water. And then we did another subtraction to get the mass of MgCl2 and then we used the molar mass to get the moles of MgCl2. Then you just put one over the other and you get the ratio. And we notice that there are 6 moles of water for every 1 mole of MgCl2. That means there must be 6 water molecules per hydrate, per formula unit of the hydrate. So that's just some pretty simple calculations. We just have to know which data, what to do with the data, right? We have to go, okay, this is the sample with the MgCl2 and the water. This is it with just the MgCl2, no water. This is just the container by itself, right? So we have to know which number to subtract from which number. That's the main slightly tricky part about what we've done so far. That's all. So, moving on, a different student heats the hydrate in an uncovered crucible and some of the solid spatters out of the crucible. This spattering will have what effect on the calculated mass of the water lost by the hydrate? Justify your answer. So, what we're doing when we're doing this experiment, we are assuming that the MgCl2 stays there in the vessel, in the crucible. Right? We are assuming that all of the mass lost is water that has evaporated. We are not making any room for error where we are thinking that some of the mass lost might be MgCl2. We are assuming that all of it is water. Therefore, if some of the solid spatters out of the crucible, we are losing mass that is not water. We're losing MgCl2. So that necessarily will mean that the calculated mass of the water that is lost by the hydrate will be too high, right? Because some of the mass that we're calculating isn't water. It's MgCl2 instead, right? So that's just a little bit of logic there. We're saying that the calculated mass of the water would be too high because some of it is not water, some of it is the MgCl2. So that's another logical one there. Now, moving on here, we're going to talk about a similar experiment. In the second experiment, a student is given 2.94 grams of a mixture containing anhydrous MgCl2 and KNO3. To determine the percentage by mass of MgCl2 in the mixture, the student uses excess AgNO3 to precipitate the chloride ion as AgCl. So we know that this is the common ion effect, right? We've got MgCl2, and so these are both water soluble. So we make a solution here. We've got these will dissociate. We'll have magnesium ions, we'll have chloride ions, we'll have potassium ions, we'll have nitrate ions. But then we add silver nitrate, and so that's also water soluble. So now we have silver ions and more nitrate ions, but silver chloride is water insoluble. So in solution, the silver and chloride ions will find each other and crash out of solution as a precipitate. So for the first thing we want to do is we want to describe the steps necessary to quantitatively determine the mass of the AgCl precipitate. Okay, so we're going to add the silver nitrate, right? We're going to add the silver nitrate and we're going to form the precipitate. So we will form precipitate. And then once we have the precipitate, we can separate this by filtration, right? Because the easiest way, if you want to separate substances, if they're in different phases, that's very easy to do. We want the solid, and we don't want the solution, right? So we're going to pour that onto some kind of a filter flask, right? A Buchner funnel or something like that, and we're going to let the solution pass through. We're going to let the solution pass through and collect the precipitate. So that's a very, very easy separation technique. We're going to do a filtration, right? Then we've got our crystals. We've got some crystals, and we're going to want to wash and dry the crystals, right? We're going to wash and dry them. We're going to wash them, meaning we're going to make sure as much of the impurity gets pulled out of there as possible, right? Because in that crystal there could be maybe other stuff stuck in there, so we want to wash that out. But then we also want to dry the crystals because we don't want any water in there, right? We're going to make a calculation about the mass of silver chloride, and we don't want any water in there to throw off our measurement. Right, we want to get a mass that it corresponds only to AgCl and not to any residual water that might be in there. So we have to wash and then thoroughly dry our crystals, and then we can get the mass by difference. Right, we can weigh whatever we're collecting the crystals on. Right, whatever kind of funnel or whatever apparatus it may be, and maybe there's some filter paper on there, whatever. We'll measure all of that first, right? We'll measure all of that first, collect the crystals, wash and dry, and then measure again, and then by difference we get the mass of the crystals, right? So this is just making sure you understand conceptually what it is that we're doing. We're forcing a precipitate to form, right? And then we're getting data about that because all of the chloride in the silver chloride came from the magnesium chloride. That's the only source of chloride in there. So now we can move to the next one. The student determines the mass of the silver chloride precipitate to be 5.48 grams. On the basis of this information, we want to calculate the number of moles of magnesium chloride in the original mixture and the percent by mass of magnesium chloride in the original mixture, right? The original mixture was 2.94 grams of some magnesium chloride and some potassium nitrate, and we don't know how much of each. But what we're doing here, we're doing this experiment to find out, when we get the precipitate, we'll find out how much chloride we've got, and if we know that, we know how much magnesium chloride we had, because all of the chloride in the silver chloride came from magnesium chloride, right? So how are we gonna do this? Well, we know that we have 5.48 grams of silver chloride. So let's get that into moles first. 1 mole, and we just get this from the periodic table. 143.32 grams is 0.0382 moles of AgCl. So now we can do a little critical thinking. This is the number of moles of silver chloride we collected. So what are the moles of chloride ions? Well, it's the same number, right? Because we have 1 chloride per formula unit of silver chloride. So we have 0.0382 moles of chloride ions. So how many moles of magnesium chloride did we start with? We're going to have half as many, right? Because each magnesium chloride has 2 chloride ions, right? So when the magnesium chloride dissolves and dissociates, whatever moles of magnesium chloride there were, we'll get twice as many moles of chloride ions. So we have to cut this in half. And so if we cut that in half, that is going to be 0.0191 moles of magnesium chloride. Okay, so we took the mass of the precipitate and we calculated the moles of chloride ions and therefore the moles of magnesium chloride from that initial sample that would produce that many chloride ions that ended up in the precipitate. So let's get that as a mass now. Now it's pretty straightforward, right? We got a little room over here. So that many moles times 95.2 grams per mole. So that gives us 1.82 grams of MgCl2, right? Oh, wait, I forgot the number of moles. Yeah, this is the answer to part 1, right? It wanted the moles of MgCl2, and we took the moles and we got the mass, and now with the mass here of 2.94, right? Now we can get the breakdown here, right? We just figured out that of those 2.94 grams, 1.82 grams were magnesium chloride, and we can divide that by 2.94 grams, and then multiply by 100, and we see that it was 61.9% MgCl2 by mass. So that would be the answer to part 2. So we're understanding that we're adding silver nitrate to provide the silver ion required for AgCl, silver chloride, to precipitate. We get the mass of the silver chloride precipitate, and then from there we get the moles of silver chloride, the moles of chloride, and then the moles of magnesium chloride that must have produced all of those chloride ions in the silver chloride precipitate. From moles we go to mass, and then we get the percentage, right? This mass over the total mass of the mixture, we get the percentage of the mixture that was magnesium chloride. So that is a nice problem about gravimetric analysis. And a lot of stuff where we have some data, we have some masses, right, in the first one, combining all of that into one nice long answer problem.